Welcome back to this third lecture on forced convection. Near the end of last lecture, we had looked at some simple correlations for fully developed heat transfer during laminar flow in a circular tube. Also, correlations for heat transfer during thermally developing flow. Let us now take some illustrative examples. The first example we look at is this. Let's say we have a tube uniform smooth tube with internal diameter d of 1.5 centimeters. Water flows through that tube at a rate of 50 kilogram per hour. The tube is heated uniformly at a uniform heat flux of 2000 watt per square meter. At some location Z, the bulk mean temperature of water is 40 degrees C. We will assume that the velocity and temperature profiles are fully developed at this location, and we have to determine what is the local heat transfer coefficient at Z, and we also have to determine what is the wall temperature at Z. First, the fluid is water. The local bulk mean temperature is 40 degrees C. So, we have to determine properties of water at 40 degrees C. These turn out to be conductivity 0.634 watt per meter Kelvin, density of 992.2 kg per meter cube, and kinematic viscosity of 0.659 into 10 raised to minus 6 meters square per second. To determine Reynolds number, we have to determine the mean velocity. This will be the flow rate divided by density divided by the flow area, pi by 4 d squared. If you substitute the flow rate 50 divided by 3600 kilograms per second, density as determined in the diameter of 0.015 meter, you will get this velocity to be 0.0792, just about 8 centimeters per second. Next, we determine the Reynolds number which is V bar into d divided by nu, and you will get this thing substituting the values of v bar, d and nu to be 1803. This is less than 2000 or say 2300, hence flow is laminar. This is the first step. Now we have laminar flow. We have heat flux uniform. We have already assumed fully developed velocity and temperature profiles, and hence we can use the result for the fully developed constant heat flux laminar flow situation in a circular tube, which will give us the local Nusselt number out there as 4.364. The Nusselt number by definition is local heat transfer coefficient into the diameter d divided by the thermal conductivity K. So we know the Nusselt number, we already know the diameter, we have already determined the thermal conductivity. So the local heat transfer coefficient turns out to be 184.4 watt per meter squared per Kelvin. That's the first conclusion. Now the heat transfer coefficient itself is the heat flux. It's uniform, so we don't have to use the subscript z, divided by the wall temperature at that location minus the mean temperature at that location. So we know the heat transfer coefficient. The wall heat flux is specified 2000 watt per meter squared. Tmz is specified 40 degrees C. So only unknown this equation is Twz, and if you calculate that out, it turns out to be 50.8 degrees C. Now let us look at some other problem, slightly different. Let us modify the situation. Let us say we have a very similar tube, in fact a very similar situation, same diameter, water flowing at 50 kg per hour. But let us say now that the wall temperature is maintained at 50.8 degrees C uniformly, here as well as here, and at some location Z, actual location Z, Tm happens to be 40 degrees C. Again assume fully developed velocity and temperature profiles, and we have to determine the heat transfer coefficient at that location and the wall heat flux at that location. Now notice that compared to the previous problem, the diameter remains the same, the flow rate remains the same, and the temperature at which the properties are to be determined also remains the same. Hence, the Reynolds number also remains the same. So, we have Reynolds number of 1803, that means it is laminar flow. And laminar flow plus T wall is some constant value gives us the situation where the local Nusselt number based on the diameter is 3.657. This will now be the nu Hz into d by k. D and K are no different from the previous illustrative example. Nusselt number is lower, hence our heat transfer coefficient will also be lower, and that turns out to be 154.6 watt per meter squared Kelvin. And the heat flux at the wall at that Z is calculated as heat transfer coefficient into wall temperature at that location minus the mean temperature of the fluid at that location, and this turns out to be 1669 watt per square meter. So, notice that uniform heat flux boundary condition gave us a slightly higher heat transfer coefficient. A uniform temperature boundary condition will give us a lower heat transfer coefficient and hence a lower heat flux. Again, I would like to bring your attention to this assumption that it is a fully developed velocity and temperature profile in this case as well as in the earlier case. Suppose the velocity or in particular the temperature profile were not fully developed, then what would happen? Remember that in the thermal entry length, the heat transfer coefficients are higher than in the fully developed situation. Hence, under the assumption of fully developed velocity and temperature profile, we have obtained perhaps the lowest possible heat transfer coefficient in either the first case or the second case. And hence, in the first case, we have obtained, because the heat transfer coefficient was perhaps the lowest, an estimate for the highest possible temperature of the wall. If the heat transfer coefficient were higher, that would be lower than the value computed. And in the second case, we have determined perhaps a lowest possible value for the heat flux, because during the development region thermal entry length, the heat transfer coefficient will be higher and hence the heat flux will also be higher. So, remember that the fully developed situation acts as a limiting situation for the entry length problem. Now, let us look at a third problem. Again, we have the same tube, and a similar flow situation. Water flows at a rate of 50 kg per hour through a tube of diameter 1.5 centimeter. The inlet temperature of water TMI is 30 degrees centigrade. the length of the tube is 1 meter. We have a fixed length of tube. The wall of the tube is maintained at a uniform temperature of 70 degrees C. Because the wall is at a higher temperature than the inlet temperature of water, water will get heated up and the exit temperature will be somewhere between 30 and 70 degrees C. Our problem is to determine what is the mean bulk temperature at the exit. Now, this is a problem where we will have to consider the average heat transfer coefficient over this length and relate the answer to that. Now, for determining the average heat transfer coefficient over the length, we will have to use properties at the bulk mean temperature, that is the inlet temperature plus the exit temperature by 2, that would be the bulk mean temperature. Now, the exit temperature is not known. So, we will have to estimate the bulk mean temperature to start with. Later on, we will check this estimate. See, the exit temperature will never exceed 70, depending on the length, whether it is short or long. If it is too short, it will be near 35, 40. If it is long, it will be 60, 65. Let us assume, just as a guess, that let the exit temperature be 50. We are not estimating directly the exit temperature, but suppose it were 50, then the bulk mean temperature for property evaluation would be 40 degrees C. Okay. We already have listed with us properties at 40 degrees C, so that is a good assumption to start. So, let us assume that T mean bulk is 40 degrees C for property evaluation. Again, I will list out the properties for water. Rho 992.2 kg per meter cube, K 0.634 watt per meter Kelvin, nu 0.659 into 10 raised to minus 6 meters square per second. Prandtl number equal to 4.31, that is dimensionless. Cp equals 4174 joules per kilogram Kelvin. We have the same flow rate, same diameter, same properties. So, the Reynolds number turns out to be 1803, which implies that the flow is laminar. Now, we have to begin heating from Z equal to 0. So, this is a thermal entry length situation. Let us calculate the dimensionless value of Z. Z star we know is Z by D divided by RED into Prandtl number. the total length in this case Z would be equal to L, 1 meter divided by 0.015 meter divided by Reynolds number 1803 into Prandtl number 4.31. This turns out to be 0.00858. Now we look at the correlations which we saw yesterday for thermal entry length. We notice that this particular value of Z star, it's smack within the range of the correlation. It's not large and beyond the correlation where we will say that look, it's almost fully developed. So we will have to use the appropriate correlation since it is laminar and it is a situation of constant wall temperature. We have this correlation. This is the average Nusselt number over the length L, which is represented by Z star, is 1.615 Z star raised to minus 1/3. This turns out to be 7.889. If it were fully developed, this would be 3.634. So this is significantly higher than that. Not quite twice, but definitely more. Why? More than twice. Now this Nusselt number is nothing but the mean heat transfer coefficient or the average heat transfer coefficient over that length multiplied by D divided by K. We know the diameter, we know the conductivity, so H bar turns out to be 333.4 watt per meter squared Kelvin. Notice that this is higher than what we obtained for the fully developed situation. Now we know the area of the tube, pi into D into L, everything is known. We now know the average heat transfer coefficient. So we should be able to determine the heat flow rate from the wall to the fluid, because heat flow rate from the wall to the fluid would be heat transfer coefficient into area into temperature difference between the wall and fluid. However, because it is a constant heat flux, constant wall temperature situation, we have a uniform wall temperature. This is the, say, the length. This is 70 degrees C. The fluid enters at 30 degrees C. And it will heat up like this, not in a straight line, but in a curvilinear fashion. Initially it will heat up fast, then it will heat up slow. Consequently, it's not easy to directly write an expression for the mean temperature difference between the wall and the fluid, because it varies from point to point. Let us do the following exercise to determine the mean temperature difference. Let us say that this is the tube. This is the inlet section. This is the exit section. This is Z equal to 0, where the temperature is Tmi. This is the exit section temperature TME, Z equals L. Z increases like this. Let us take a small slice and consider it as a control volume. In this control volume, thickness delta Z. So one wall is at Z, another wall is at Z plus delta Z. We will now apply to this the first law of thermodynamics. Flow takes place at a rate of m dot. So the heat absorbed must equal the outflow of enthalpy. How much is the heat transfer from the wall to the fluid? That will be the mean heat transfer coefficient. Once having calculated the mean heat transfer coefficient, we assume that that is the heat transfer coefficient applicable everywhere, multiplied by the area of heat transfer in this slice, that will be pi d delta Z, multiplied by the local temperature difference, that is the wall temperature. We need not use a subscript Z, minus the local mean temperature Tm. Or Tm at Z. And this should equal m dot into enthalpy out minus enthalpy in, and that would be equal to m dot into Cp of the fluid into Tm at Z plus delta Z minus Tm at Z. Transposing terms, notice that this can be written down as dTmz. We will get dTmz divided by T wall minus Tmz equal to H bar pi d delta Z divided by m dot Cp. This delta Z can be considered a small slice dz. Now we integrate either side from Z equal to 0 to L. The resulting equation is log of Tm exit minus T wall divided by Tm inlet minus T wall equals minus H bar pi d L divided by m dot Cp. Now notice that in this expression we have the values of everything except TME. Wall temperature is known, inlet temperature of the fluid is known, heat transfer coefficient has been calculated, D, L, m dot are specified, Cp has been determined. So if you substitute, you will get ln Tme minus wall temperature of 70, 30 minus 70 will be equal to minus H bar, that was 333.4 multiplied by pi multiplied by 0.015 multiplied by L, that is 1 meter, m dot, which is 50 divided by 3600 kg per second multiplied by Cp, which is 4174. Solving this for TME, notice that the right hand side is negative, and that means this argument of the logarithm will be a number less than 1, and that means the numerator will be smaller in magnitude than the denominator. The denominator has a magnitude 40, so the numerator will have a magnitude less than 40. So, TME will be higher than 30, it will be somewhere on the side of 70, higher than 30 but lower than 70. And if you calculate TME, that turns out to be 53.8 degrees C. Now, we started off by having assumed the bulk mean temperature. We needed that assumption to determine the properties. We had assumed 40 degrees C. Let us check that assumption. The bulk mean temperature now turns out to be inlet bulk temperature plus exit bulk temperature by 2, average of inlet and exit. This turns out to be 41.9 degrees C. We had assumed 40 degrees C. It is different, higher by about 2 degrees C. Properties will be slightly different. If one insists, one can now recalculate the properties at say 41.9 degrees C, go through the same exercise, and maybe you will get a slightly improved value of TME. If this assumption were to differ from this calculated value by a very significant amount, say 10 degree, 15 degree, then it is definitely worth redoing the calculation with the new corrected value of the bulk mean temperature, because the properties would change reasonably significantly. With a temperature difference of about 2 degrees C, they are unlikely to change, but anyway it may be a good exercise for you to check that out. After having studied laminar flow through a tube, let us now look at turbulent flow heat transfer in a tube or a pipe, circular one. Unlike laminar flow, because of the eddies formed during turbulence and turbulent mixing, turbulent flow is invariably difficult to analyze, much more difficult than laminar flow. And hence, we obtain information for turbulent flow essentially from experiments. And all the correlations, or almost all correlations which we have for turbulent flow, are based on experimental data. In a way, turbulent flow is slightly simpler, because in turbulent flow, the effect of the boundary conditions are small. We notice that for fully developed boundary condition in laminar flow, fully developed profiles in laminar flow, we had significantly different values of the Nusselt number, depending on whether the boundary condition is that of uniform heat flux or the boundary condition is that of uniform wall temperature. In turbulent flow, because of the mixing of all laminae, this difference reduces significantly. You will hardly ever find a correlation in turbulent flow specifically for say uniform wall temperature boundary condition, or specifically for uniform wall heat flux boundary condition. Almost always the single correlation is applicable to both. Again, because of turbulent mixing, the effect of the entry length is small during turbulent flow. Laminar entry lengths tend to be larger, they tend to increase with Reynolds number. Turbulent entry lengths are usually smaller and they do not have a significant effect of Reynolds number on them. For turbulent flow heat transfer in a pipe, perhaps the famous, historically important, is the celebrated Dittus-Boelter correlation, more than 75 years old, but it is still being used because it is simple, straightforward and works reasonably well. The Dittus-Boelter correlation provides the local heat transfer coefficient under fully developed conditions, and the equation is reasonably simple. The Nusselt number is a function of Reynolds number and Prandtl number and is equal to 0.023 into Reynolds number raised to 0.8, Prandtl number raised to some exponent n, where the exponent n is 0.4 for heating and 0.3 for cooling. So, heating data correlates well with n equal to 0.4, cooling data correlates well with n equal to 0.3. For this correlation, we will have to determine properties which are evaluated at local bulk mean temperature to determine the local heat transfer coefficient. But if you are considering an average heat transfer coefficient over a length, you must use the bulk mean temperature over that length. It is reasonably wide in its validity. Prandtl number going from 0.3 right up to 100. So, water is included, air is included and some not very high viscosity oils are also included. And Reynolds number in the turbulent zone from 2300 to something like 120,000. Of course, the Dittus-Boelter correlation is pretty old. We are attracted to it because of its simplicity. The current recommendation for the most suitable correlation is the Nielinski correlation. It is also about 25-30 years old. Notice that here the Nusselt number is provided as a function of not only the Reynolds number and the Prandtl number, but also the friction factor for flow through that tube. And the friction factor itself will have a dependence on Reynolds number. So, it has a reasonably complicated dependence on Reynolds number as well as Prandtl number. This also provides the local value of the heat transfer coefficient when the velocity and temperature profiles are fully developed. Again, like the Dittus-Boelter correlation, the properties are evaluated at the local bulk mean temperature. It has a slightly wider validity, Prandtl number going from 0.5 to 2000. So, some reasonably high viscosity oils are also included. The Reynolds number going from 2300 to 5 million. This also is a higher range. Depending on the smoothness or the roughness of the pipe, this can be applied by using appropriate correlation for F. For a smooth pipe, you use a correlation for F which pertains to smooth pipe. For rough pipe, the effect of epsilon by D or E by D can be included using the Chen's correlation. So, the effect of smoothness or roughness of the pipe is included through the effect on F. Let us take an illustrative example based on the Nielinski correlation. We are now going to look at the same old pipe with which we were playing around. We have a tube of some length L, which we are going to determine here. It is given that the diameter is 1.5 centimeter. The wall temperature is maintained everywhere at 90 degrees C. The inlet temperature is 50 degrees C. We want the exit temperature to be 65 degrees C. So, this is a design problem where we are not given the length of the pipe, we are given the requirement that the exit temperature should be 65 degrees C, and we have to determine the length of the pipe. The fluid flowing through this is water, and the velocity is 1 meter per second at inlet. One thing is straightforward here. We know the inlet temperature, we know the outlet temperature, we have to determine the overall length. So, we are talking of a situation where we will have to determine the average heat transfer coefficient. We know the inlet temperature and outlet temperature. So, we can determine the bulk mean temperature 50 plus 65 by 2, which is 57.5 degrees C. And at this, for water, the following properties will be interpolated out. So, at 57.5 degrees C, the properties of water are density 984.4 kg per meter cube, kinematic viscosity 0.497 into 10 raised to minus 6 meter square per second, Cp 4178 joule per kilogram Kelvin, Prandtl number 3.12, conductivity 0.656 watt per meter Kelvin. Now, we need to know the velocity at the bulk mean temperature, where the density is 984.4. What is specified is velocity at inlet. So, we need to determine at inlet density will be density at 50 degrees C, and this turns out to be 988.1 kg per meter cube. Using this density and the velocity at inlet, let me call this V bar I, we get m dot is rho at 50 degrees C multiplied by pi d squared by 4 area multiplied by the mean velocity at inlet. This turns out to be 0.1746 kilogram per second. And based on this, if we calculate velocity at the bulk mean properties, that is at a density of 984.4, this will turn out to be m dot, which is calculated, divided by pi by 4 d squared into rho, where rho is 984.4. We will get a slightly higher velocity, which is 1.0038 meters per second. It is this velocity which is determined at mean properties that we will be using to determine the Reynolds number. The Reynolds number is now calculated as V bar d by nu, that turns out to be 30295, which is well in the turbulent zone. Prandtl number is already greater than 0.5. So, in principle, the Nielinski correlation should be applicable. For that, first we have to determine the friction factor. Assuming the tube to be smooth, there is no specification of any roughness. We will use the smooth tube correlation 0.079 RED raised to 0.25, which is the recommended correlation for smooth tubes to be used with the Nielinski correlation. We will get 0.005988. And if you use the Nielinski correlation, you will get the Nusselt number, which, because we have determined it at average properties, the average Nusselt number, which turns out to be 152.98, which is h bar d by k, from which we get h bar equal to 6690.3 watt per meter squared Kelvin. See the high value, a few thousands for this. Now we have our relation for a uniform wall temperature situation, log of Tme minus T wall divided by Tmi minus T wall equal to minus h bar pi dl by m dot Cp. Now we have been specified Tme, Tmi, Tw, left hand side is known. We have determined h bar, we know d and l, we know d, we know m dot, we have determined Cp, L happens to be the unknown. So, solving this equation for L, we get L to be 1.088 meters, nearly 1.9 centimeters. Remember that for the average, the local heat transfer coefficient to be used for the average value, we need L by D to be greater than 60. If we determine L by D, this turns out to be 1.088 divided by 0.015. This turns out to be something like 72.5, which is greater than 60. Hence, h bar is a good estimate. That means the effect of entry length is small. With this, we come to the end of this lecture, and with this we complete the basic study of force convection heat transfer through a tube. In the next lecture, we begin a study of heat transfer from a flat plate exposed to a free stream. Thank you.